Lesson 10, vector addition. All right, so we're going to get into vectors now. We're going to start off by doing vectors in one dimension. Just give a little background, though, about what vectors are. We talked about vectors as being things like velocity, right, where it said direction matters. And before, we were talking about, whether something was going to the right or the left or up or down, or maybe it was east or west or whatever. It's really going to be the same thing now. We're going to have vectors, but now we're going to represent them with arrows. And we'll see in a minute that we can start to put those arrows like on sides and stuff too. But for now, we're going to do vectors just in one dimension. One dimension just means like that way, right? Just left and right on the paper. So that's what we're going to start off with. A couple of things that you need to know when we talk about vectors. We call the tail end of the vector the back end here. Be careful where I draw arrows now. We call the tip the front of the arrow there. Okay, the length of the vector represents its magnitude. So the longer we make this arrow, we're saying that the magnitude is bigger. So if it was just a little teeny little arrow, that means it has a small magnitude or small number. All right. So as we saw in lesson 2, motion in one dimension involved vectors that are collinear. It just means along the same line. So just to give you kind of like an idea of what we might be talking about here, let's say that like arrow A, that might be the speed that you were, let's say, running, or the velocity, I guess, because it's a vector. And then arrow B might be the wind that's at your back or something. So the two of them together are like adding up to something else. So just to give you a little bit of context there. So collinear means that they are just in the same plane, right? So these ones are also collinear, just in opposite directions. So this might be like running against the wind type of a situation. All right, so when adding vectors, this is important, we add them tip to tail. So what I mean by that is, let's say, we got down here, we got vector A and vector B. You can see that vector B, the tail of vector B, is going to be attached to the end of vector A, or attached to the tip of vector A. And then that's how we add them. And then the resultant vector, we make that like an R. That's going to be from where you started to where you ended. And we just kind of draw that like that. So if we look at this scenario, though, vector A was going to the left to begin with. And then vector B, tip to tail. So the tail of vector B is at the tip of vector A. And it's going back the other direction. And again, the resultant vector, really the net result of these being added together, is going to be from where you started to where it ended. And that's going to always be the case. And I'll show you. I got this little simulator thing. Can I scroll up and down? No, I cannot. Well, I want to show you the top of this thing because it's got some numbers up top, but I didn't make my screen big enough to actually see it. But I can show you what I need to from here, and maybe I'll make another video here in a minute with the top showing. But okay, so there's one vector we've got in red there, right? So that might be like a displacement. That could be like a velocity. It's just some arrow that we said is going to the right. Okay, now I can grab another arrow. And let's say that I had that arrow, just above it. And I put it like, tip to tail like we said. So it's going to be something like that. Then if I go show sum, it gave me this green arrow over here, but like one thing that people seem to have a hard time with is they're like, yeah, but that's not over here. But it could be written over there. One thing that's kind of, you have to start to figure out about vectors is you can move vectors around wherever you want. I can have this vector over here and that one over there. Oh, not move them though. And it doesn't matter. Their resultant vector is still going to be this arrow in that direction, and it's going to be that length. So you can like move these things around. That might take a little bit of getting used to get the idea behind that. But yeah, okay. Hopefully that made sense. I'll go back to my thing now. All right, zoom in. Okay, yeah, here, just a little warning that they have to be the same type of vector to add them together, though. I can't add displacement and velocity. I can't like say something's moving 10 meters per second that way and then add 5 meters the other way. Like it doesn't make any sense. So it has to be the same. Okay, so there are going to be two ways that we can solve vector problems. First is graphically, and the second is going to be algebraically. I'm going to show you graphically first. All right, so a person walks 20 meters west, then 15 meters east, and finally 10 meters east. What's the person's final displacement? So the graphical way, we're going to choose an appropriate scale and choose a reference direction. So the scale here, this is really just so we can fit it on the page. We're going to call every 5 meters in this question, we're going to call every 5 meters 1 centimeter, just so it fits on our page. The direction, we're going to call east positive, we're going to call west negative, like we usually do. So we're going to draw the first vector and label its magnitude and direction. So this vector here, this would be something that you draw out with a ruler. And if I have this labeled as negative 20 meters, so this negative 20 meters here, this would actually be drawn out as, well, 20 divided by 5, right? That's how many centimeters this would be. So on your ruler, this would actually be 4 centimeters from that end of it to that end of it. And you'd have to measure it out properly. So 4 centimeters from there to there, and you can label it as negative 20. Okay, and then we're going to start our next vector from the tip of the first one, but now it's going to the right because it's going east, and it's going to be 15. So I go 15 divided by 5, so 3, so it's going to be 3 centimeters going that direction, right? And then the last one would be 10 meters, so that would just be 2 centimeters that way when you actually measured it with a ruler. And then what you have left here, scroll down a little, the resultant vector here, that's going to be from where you started to where you finished. And then if you measure that with a ruler, that it would end up being 1 centimeter in length. So you measure that with a ruler, and then we just have to multiply by 5 meters again to get back to our meters, like back to the actual ratio that we want. And it's going to the right, it's positive, so we'd say this is 5 meters east. Algebraic vector addition. You might have been kind of doing this already. Technically, I kind of like this one better. It's just less measuring and stuff like that, like you're not used to doing. This one, we're going to do the same thing. We're going to call east positive, west negative. It's more like what we've been doing. So you're just going to add the vectors together using the appropriate directions. So we're going to say the resultant vector R, you could also call it D, that just means the same thing, right? Is going to just be all the vectors added together. So this would just be 20 meters west, so that would be negative 20. Maybe I could write this out here too, negative 20 meters. This would be plus 15 meters and then plus 10 meters. So we'd end up with a positive answer here, 5 meters positive, so it would be 5 meters to the east. So this is probably a bit easier method.